Hey there, everybody. Whoa, sorry, that looked a little wonky there. There we go. Welcome to your second installment of Metabolism. We're continuing on from where Rebecca left off with Krebs cycle. We're gonna jump right into oxidative phosphorylation, electron transport chain. What's going on, team? Guten Tag, Alejandro. Good to see you. Bunch of familiar names. Welcome back to the crew. Um, so I know, right? I actually before class I was telling that to Patrick that I was going to try to have the weirdest hair possible for class tonight. So I'm just going to go with it. So actually that just looked way too weird. That's okay. But one thing I do want to warn you in today's class is that there is a ton of stuff that we're going to go through today. So just to warn you, this goes pretty fast. So ideally, remember with all these, especially these really intense, real deep content channel sessions like the metabolism stuff, you really do want to come in with the foundations already in place, and then we'll basically reinforce them. If you're coming in totally blind, you haven't really done any metabolism ever before, that's fine, but don't expect to walk away from here having a complete understanding of everything. So what I'm going to focus on is not the nitty-gritty details. I'm going to give you guys like the real big take-home points, the easiest way this stuff shows up on the MCAT, basically how to get the most bang for your buck without getting too granular with the little nitty-gritties. So that'll be kind of like the plan for today. All right, so in terms of structure for today, we are going to start off going into the electron transport chain. There's a lot that goes into the electron transport chain, so we're going to pick out the key details, the things that matter the most, as well as a couple of things you can get the most points for the least amount of memorization. After that, we'll change gears. We'll talk about the key enzymes and glucose balance. We'll talk about gluconeogenesis, namely, so that'll actually touch back to what Rebecca just covered in glycolysis. We'll talk about the reverse. There'll be a couple key enzymes that we will need to know from glycolysis, but only really the key reversible enzymes. We'll get to that kind of soon. After that, we will, of course, move on beyond gluconeogenesis and talk about glycogenesis as well as glycogenolysis, which is the breaking down of glycogen. We will likely move through that last part pretty quickly and just hit a couple key points. So, all right, let's get this party started. As you know, we've got Patrick's gonna be running most of the Q&A. Andrew's here as well as Liz. If you have any questions, let us know. If you do want to get granular, if you want to get nitty gritty, just hit us up. Q&A is there for anything that you want to talk about. But as I said, I'll try to just go big picture as much as possible in today's class. All right, so as you can see, electron transport chain, super easy, not that much going on, right? Or not. Yeah, prepare yourself, Ariel, right? Oh my god. All right, so let's just talk general structure. Where do you find this? Where is this thing even? Let's get real big first. We're going to try to hit the highest yield, most important stuff today. Which membrane specifically, though? It is remember, it's the inner mitochondrial membrane, which means it's the membrane that separates what two things. This is the even higher yield stuff, so I'm going to try to get the real kind of big guns, as we say, in terms of points. So it's the membrane that's separating the matrix as well as the intermembrane space. Nice work. Sarah, Valerie, a bunch of folks are all saying it perfect. So that's probably your biggest, most important thing. So basically what the electron transport chain is a series of oxidations and reductions. So even here, this is some other more high yield important things. Oxidation means what once again? Because this entire class is going to be focused on it, so let's get the big points out of the way. Loss of electrons. Any favorite mnemonics for that? Because there's a couple different ones. Valerie likes oil rig, and Maya likes Leo goes gur. So it's either oxidation is loss of electrons or gain of electrons, or you could do Leo goes gur, which is loss of electrons is oxidation. They mean the exact same thing. Understandable, Abigail. There is a lot of oil rigs in Texas. Cool. All right, so that's what this is all going to be based on, is basically moving things back and forth. The main thing is, though, when we talk about oxidation, well, like let's actually, we'll get to the first step here and actually kind of show where this is. There we go, FADH and FADH2. So how in the heck do these things actually do, oxidation or reduction? What are we moving? Is it electrons? I mean, what are we really moving here? Yes, Valerie, it's electrons via, why does it go from NADH to NAD+, though? I mean, that seems weird because it's not just talking about gaining or losing a charge. We're losing an entire atom there. Yeah, there we go. What do you call that H minus? You guys are saying H minus in the chat. Hydride, exactly. So what is a hydride? Remember, is when you have a proton, of course, with a lone pair on it. So we're basically talking about shuttling hydrides as well as protons when we get to the proton motive force back and forth. Yeah, exactly. So like that's FNADH, it really means hydride. Same thing when we talk about, for example, a reducing agent. Anyone have a common reducing agent they want to think about or call out? We'll get into these in the orgo class next. There's a couple of classic, yeah. Lithium aluminum hydride, right? LiAlH4, right? So same thing. If it's a reducing agent, it's not protons it's hydrides that it has. So this will be the kind of like big picture, high yield stuff that I'll try to focus on as we go through today. But if you want to get more and more granular, hit us up in the Q&A. We can get detailed too. All right, so those are our main electron donors, and of course oxygen is the final electron acceptor, which makes sense because it's a pretty darn electronegative element. It wants electrons, right? So it's happy getting, of course, reduced. All right, of course the objective is to establish a membrane electrochemical gradient. So we're going to get into this a lot today. We'll do it later on when we start talking about the actual oxidative phosphorylation, but it's the exact same when we talk about neurons, right? Neurons also focus on electrochemical gradient. It's when you have two different forces driving ions in one direction, both concentration differences as well as, of course, electrical differences. Let's actually connect it right now. So when an action potential begins, what's the electrical chemical gradient that's actually moving stuff? What's moving and why? I'm going to try to connect it to other topics, really. We'll do the spiderweb theory of learning today as much as possible. Sodium influx, exactly. So remember, the membrane it's negative, of course, inside the cell. So when you open up those sodium channels, sodium floods in because it's negative inside the cell, and also because your sodium, potassium, ATPase pumped all the sodium out, so it wants to come in because of that concentration difference too. It's the same thing here in the mitochondria, just instead of sodium moving, or potassium in action potentials, it's protons. And so the more that you connect this to the other parts of science, the other bio and biochem topics, the easier it's going to be not to think of this as disparate random topics, but all part of this exact same general idea, just different aspects of that same general idea. And that's the highest yield of everything. So that'll be the focus. All right, so we'll get a bit granular. We'll focus on our very first complex here. Of course, there's an interesting thing about complex 1. And if there is one thing that I want you to really take out of this that's very specific to ETC, know the differences between complex 1, 2, 3, and 4. Those are very, very easily testable differences. And so we're going to focus on the key differences, not the little, specific things going on here, but the big differences. All right, so now there is something that's very unique to complex 1. It's the only place that uses something that's very important. The complete intake of only complex that uses this directly, NADH, exactly, Sarah, you guys got it. So it's the only one that directly uses NADH, and as you saw in Rebecca's class with the Krebs cycle, we make a ton of it. So this is a super important complex. It's our input of course, NADH into the process here. That looks a little weird on my screen. I think you guys can still see it there, but that looks a little wonky. Is it the same on yours, Andrew and Patrick? Look kind of whited out. It's okay. It is whited out. Okay, that's kind of strange. That's all right. As long as it's visible, right? There we go. As long as you can see it. Oh, that's why it's going to fade it in as we go. Okay. So I was confused. I'm like, wait a second. I thought there was supposed to be a formula there. All right. So the main thing here is, of course, we have NADH coming in. And so notice, of course, what it's going to do is it's going to transfer its electrons to FMN. There we go. Which is a flavin mononucleotide. So it transfers it into there because the thing is NADH is pretty big, right? You don't want to actually move the entire thing in. So it transfers, of course, the electrons into there right there. So basically, it's this is a flavoprotein. It has a coenzyme called the flavin mononucleotide. But so this is a flavoprotein in general. Of course, it's just the coenzyme that actually does the accepting of the electrons here. So of course, it might be the same root. I don't know if flavoprotein, if it flavor. I'm wondering, actually, though, it might have a similar root. I'm curious if Andrew or Patrick have actually, or if Liz has heard about this, but we'll get into the, we have more, it's not balanced yet. Yeah, we'll get into a final balanced equation, Ian, but don't even worry too much about the equation itself. It's more the big picture here. So the main idea here is that the NADH is going to transfer it to your FMN, so your flavin mononucleotide. Which is then going to transfer it even further to actually reduce an iron-sulfur subunit. Then that iron-sulfur subunit is going to donate its own electrons to coenzyme Q, which is a very important thing that you need to know the name of. What is coenzyme Q? So basically, these electrons get transferred all the way down from flavin mononucleotide, your iron-sulfur complex, all the way that to your coenzyme Q. What? It transfers it to ubiqua, and the word roots. Exactly, ubiquinone. And once it gets reduced, what do you call your ubiquinone? Ubiquinol. Nice work. So now the cool thing here is we can actually use our word roots to figure all this stuff out. As you're passing down these electrons and actually getting it reduced, think about your word roots. If you compare ubiquinone to ubiquinol, well, let's think. If you ever end in "one," what are we thinking first and foremost? Ketone, exactly. So if you've got a ketone versus all alcohol, what's more reduced, a ketone or an alcohol? The alcohol, exactly. So that's why, of course, the oxidized form is ubiquinone, and of course, once you transfer your electrons there, or your hydrides more specifically, right, you turn it into ubiquinol. But the cool thing is, even without memorizing stuff, the nice thing is, on the MCAT, it's a multiple choice test. If you know your word roots, you can figure out what the answer is going to be, because if you know it's reduced, it sure ain't going to end in "-one," because that's a very oxidized molecule. All right, so there's two really great things for you to take away from this. So there is your full balanced equation, as we were asking before. Actually, no, there's one more step. We have the net on the bottom. There we go. So there's your mechanism. The full net, of course, is on the bottom there for you. But the idea is, through moving these hydrides from NADH to ubiquinone, we have two main things that happen. Number one, you're going to move 4 protons into the intermembrane space. Secondly, you're going to make some ubiquinol, which then we can use in a future complex. So for those of you that have read ahead and know this, what complex is going to utilize that ubiquinol to further the electron transport chain? Nice, complex 3. The succinate one's actually complex 2, yeah. But yeah, so complex 3 is the one that actually utilizes the ubiquinol. And we'll get to the succinate in a second. So two things are really awesome here, right? So that, and then why also is the protons a good thing? Why are we happy we just pumped 4 protons into the intermembrane space? Yeah, exactly. We can use them later. They create the electrochemical gradient. They create the proton motive force. And so the whole idea that we're doing here is most of these complexes, not all, and this is also some of the most testable stuff, which complexes are going to move protons, which are not, which are going to use NADH, which are going to use FADH2. That big picture is going to give you the most points on test day. But so the whole idea is we move these protons into the intermembrane space, which does what to the pH of the intermembrane space here? Okay, it is working good. So here's the funny thing. This is one of the traps. If anyone makes a mistake on test day, it's usually something that you know well, but we just answer quickly, make a silly mistake, because as you're all saying, right, yeah, it's going to get more protons, it gets more acidic, which means the pH goes down. That's the kind of stuff you really got to be careful with on test day, because a bunch of people said increase. Yes, the acidity increases, but you have to be very careful with the way that the question is phrased. That's why I like to ask little trick questions like that. But you got it. So of course you're going to increase concentration of protons, and by increasing the concentration of protons, you're going to decrease the pH of the intermembrane space. So we'll continue the gradient all the way across. All right. So that's awesome. We'll come back to the protons soon. We'll talk about the full picture and why they're useful and what they end up doing. Also, do you all know how to take screenshots? I mean, you don't have to. The same stuff's in your review notes, so you don't have to screenshot it. But if you ever want to today, on a Macintosh, it's Command-Shift-4, gives you little crosshairs you can click and drag. And on PCs, there's a print screen button you can click to take pictures of anything that we really go through today. All right, so that's complex 1. Only places use NADH. Notice that we're both creating ubiquinol as well as moving protons into the intermembrane space. That's honestly your highest yield, most important thing to know about this complex. All right, so let's move on to complex number 2. So complex number 2 is very unique. In fact, I'd probably say that complex 2 is the most unique of all of them here because it's also part of something else. What else is complex 2 actually part of that you just saw in the previous class? The Krebs cycle, the TCA cycle, or the citric acid cycle. There are so many names to describe that cycle. There's also a really good, I don't know if you guys have seen this yet, but if you YouTube thrift shop Krebs cycle at the same time, there's a really good, what do you call that when it's like a song that's made to a nerdy thing? It's like a spin-off, or what do you call it? Parody, there we go, it's parody. It's amazing, it's hilarious, Patrick has seen it before, it's really good. I want to warn you, the song will be stuck in your head for days. But to be totally honest, it actually helped me kind of memorize the steps of the Krebs cycle because it's a parody to the song Thrift Shop, the Macklemore song. It's awesome. It was a student at some school made it. It was fantastic. But yeah, if you just honestly type in YouTube thrift shop Krebs cycle, you'll find it. It's the first thing that pops up. So we don't even need to give you a link. But yeah, please actually don't even put the link in the chat. I prefer not to if you guys don't mind, just because people will click it and they get distracted. Search it later on. Search it later on. All right, so with that stated, oh, for sure, you're very welcome. So this is part of the Krebs cycle, right? So this, of course, is, wait, what is this? Changes succinate to fumarate. We should know this enzyme by name. We just covered this in our last class. There we go. It is, there we go. It's succinate dehydrogenase. And so here's the cool thing about all the enzymes of your Krebs cycle, that, and actually glycolysis as well. If you get good at the word roots, every single time that you see a dehydrogenase, what we're basically working with is either NADH or FADH2. And since it's a dehydrogenase, this is the site, and actually the only site, that we get FADH2. And so this, of course, is also part of the Krebs cycle. And it's the only part of the Krebs cycle that happens on the inner membrane. The rest of it happens where? Where's the rest of the Krebs cycle occur? Not on the membrane itself, but in what region? Yeah, or in the matrix, exactly. Not with Neo, but you know, the mitochondrial matrix. All right, so succinate dehydrogenase, there we go. So it's going to turn succinate to fumarate, and in doing so, of course, we create our FADH2. It's another reduction reaction, similar. If you want to geek out, throw it into the Q&A, Ian. It is another reduction reaction, so that is pretty similar. That's a good point. Because, yeah, once again, though, you notice you're using your word roots, right? And it's really all about knowing which word roots mean which things. Like, for example, if you ever see kinase, like there's a bunch of different kinases, right? Like hexokinase is for starters. What do those all mean? Like, you really just want to get good with word roots and breaking it down. Yeah, it's doing something with a phosphate, exactly. So it could be GTP, it could be ATP, but it's working with phosphate groups when it says kinase, exactly. So the more you just get the basics and the big picture and know your word roots, you can really, the MCAT's a multiple choice test. You don't have to write out the answers. As long as you recognize, you'll at least be able to narrow it down to 2, if not 1 single answer choice. Cool. All right, so that's just big picture stuff. So here, of course, is our succinate, right? So basically, it's your succinate dehydrogenase, as we said before. But the whole idea is here, notice what we're doing, of course, is you're creating FADH2. And then those FADH2's electrons, of course, getting transferred, once again, to your iron-sulfur complex. That iron-sulfur complex then, of course, passes the electron down once again to ubiquinone, which then, of course, once again, becomes ubiquinol once it's in the reduced form. Then that ubiquinol, same thing as before, goes where? Complex 3, exactly. And we'll get to complex 3 in a second. But so here's the if there's one thing to, well, there's several things to know about complex 2, but the couple things that are very unique, notice that this is the only site in the electron transport chain where hydrogens are not pumped. So you got to memorize that. That's a big high yield point. It's also the only part that's part of the Krebs cycle as well, and the only part where we actually utilize FADH2. So complex 1's NADH, complex 2 is FADH2, and of course complex 2 is the only place that protons do not get pumped. This is the kind of real high yield, most important stuff for you to memorize because it's the easiest stuff for the double AMC to test. And so it's not necessarily knowing your full balanced reaction. It's really more about just big picture stuff and how can you eliminate your answer choices to get the, of course, narrow it down to hopefully a single answer choice left over at the end. All right, so I won't get into the fumarate stuff. You guys know, of course, after that, we go through the entire rest of the transport chain back to oxaloacetate and then repeat over and over and over again. But we'll get into that a little bit more at the very end when we talk about gluconeogenesis. We'll get back to our oxaloacetate and how we can get back to where we started. All right, complex 2. Those are the 2 things to know. All right, moving on to complex 3 now. So the thing is, the way this is drawn, I know that it shows complex 3 twice. The reason that it shows complex 3 twice is because it actually happens 2 times. So don't think of this as like 2 separate channels doing it. It's 2 different moments in time. It's just drawn twice to kind of show the process on both times. All right, so complex 3, of course. Once again, this is changing gears now. So remember, complex 3 utilizes what, once again? We were making a bunch of it in complex 1, complex 2. I'm really going to hammer in the key points. Your ubiquinol, exactly. So we take our ubiquinol, it enters complex 3. And so, of course, it transfers it to cytochrome C. So this is where cytochrome comes in. I know we use cytochrome a bunch, and so this is where it's basically introduced into the transport chain. All right, so of course it transfers them. Notice the cytochromes are just proteins with heme groups on them. Basically, it reduces the iron 2+ to iron 3+. So it's sorry, the reduced 2+ would then get, of course, oxidized to iron 3+. All right. Once again, word roots, right? So it's oxidation versus reduction. The more positive charge that it has, the more oxidized it is. The more negative charge it has, of course, the more reduced it is, you could say. All right, so cool. I guess the main idea here then is notice what we're really doing, and this one looks a little bit funky, but the idea is as we go through, what we're doing is notice you've got your ubiquinol actually has two different hydrides. We got two different proton or electrons that we actually want to transfer here. And so notice when we go in, first of all, it's going to transfer one of its electrons to the cytochrome. So cytochrome gets reduced, first and foremost. Secondly, it actually transfers its electrons back to another molecule of ubiquinone. And so notice your second step, well, first electron, of course, goes to cytochrome. Second electron, though, goes back to another, of course, ubiquinone, which then we can eventually turn back into ubiquinol, which we will soon, and we'll show you how that works. So it's kind of a recycling process. So one electron reduces cytochrome, the other one loops back to your ubiquinone. Then notice that's, of course, step one. You also, in this process, are going to pump two protons into the inner membrane space. Most importantly, you're moving protons again, right? We're building up that electrochemical gradient, that proton motive force. That's the key there. Secondly, though, we got another molecule of ubiquinol. So then your other step two, this is ubiquinol now, once again, transfers its first electron again to your cytochrome. And after that, it transfers the second electron to that same molecule of ubiquinone. So notice here, of course, it's neutral. It gains the negative charge from this electron. So sitting here, it's already got a negative charge. So at this point, it's now going to take a second electron, giving it a -2 charge. Once you got that -2 charge, it can pick up these two protons from the matrix and, of course, then reform another molecule of ubiquinol, which then could, of course, loop back again and enter the cycle and, of course, create more energy, namely more reduced version of your cytochrome. Cool. Yeah, actually, we did that pretty quick, so if you want to snag that real quick. It's a little messy at the bottom there, so it's a little funky, but feel free to snag that. It's the same idea, though. We're just kind of showing it step one and step two, how it's the same idea. But so let's do kind of big picture idea. Big picture is you're going to, of course, reduce two different cytochromes, right? We're going to pump two protons the first time. We're going to pump two protons the second time. And then in the end, we're actually going to recycle, I guess you could say, or reproduce another one of those molecules of ubiquinol. There we go. So notice, of course, input of those two protons, as we said, goes to that -2 charge, right? Now it's got a -2 charge, thus picking up two protons, which then, of course, forms your ubiquinol right there. All right, so if there is a big take-home, most important thing for you guys to know right here, it is, of course, to know that complex 3 is unique because, well, it's using our actual ubiquinol now. We're changing gears and we're starting to reduce cytochromes. Remember, before we were just oxidizing ubiquinone, now we're oxidizing reducing cytochrome. And we also did pump protons. So to give you your net there, what we're effectively doing is, of course, moving protons as well as, notice we've reduced your cytochrome, because notice originally it was 3+, now it's become 2+. So we have the reduced version of cytochrome as well as moved protons into the intermembrane space to once again build up that proton motive force. So we could, of course, we'll show what happens next with those. When we talk about the proton motive force and actually creating energy from it. But that'll be our very final step when we get into oxidative phosphorylation. All right, so that's the first three complexes. Complex 4 now, very last step here, where what happens again? What's the final thing that happens here in the electron transport chain? Nice, exactly, yeah. So oxygen, of course, is the acceptor, thus producing water. Exactly true, you got it. Okay, so oxygen is the final acceptor, and as you can see, that actually oxygen is going to effectively does become water. So exactly true. Cool. All right, so last step. So notice what we're doing now is we're taking the cytochrome that we made in complex 3. That cytochrome is going to once again transfer its electrons. So it's basically the same thing. All we're doing is passing electrons down the chain, right? And so what it's going to do, of course, is pass its electrons now to copper ion specifically. Copper then passes it to iron. Not as important here, but the main idea is that we're once again passing electrons from cytochrome all the way down from copper to iron, all the way back to oxygen. Oxygen is the final acceptor, and then it becomes water. But what's the point? Why do we bother to do this? Why are we going to move electrons onto oxygen? What's the benefit of this complex? Bingo, Valerie, you got it. Though, at least in the metabolic reasons, what we're effectively going to do is, once again, pump protons. So then through passing these electrons down the chain, yes, we produce water through, of course, the reduction of oxygen, but namely it's to move more protons. And this is the last step because once you make water, water is no longer a high energy molecule. It doesn't have any electrons that it wants to transfer one way or the other. And so it's really through making these protons move into the intermembrane space is the reason that we're doing this. All right, so your net reaction right there then, of course, we are taking our water, taking our protons, moving them into the intermembrane space, and making water molecules. So I know there's, of course, way more we could talk about this stuff, and we could really get deep and really get granular, but the point is that you don't have to for the MCAT. Yes, they're going to test metabolism, but it's a multiple choice test. And so you got to think, all right, what are the big points here? What are the sticking points? And it's kind of like what Rebecca was saying with the glycolysis. You mostly need to focus on what steps are irreversible, right? What are the big control points? That's the same thing here. So know what complexes' main steps are, which ones are pumping protons. In fact, let's do a quick recap. Which complexes pump protons again? See, I'll show you guys you actually know all the key testable points. 1, 3, and 4 pump protons. What makes complex 2 unique? It's part of the Krebs cycle, exactly true. It's your succinate dehydrogenase. No protons are pumped. It's the only place it uses FADH2. And what do we create, though, again, in your second complex? What was the point of doing this here if we're not moving protons? What do we make? Nice, ubiquinol, perfect. How about complex 1? What made complex 1 unique? Got a CoQ, turns into CoQ H2. It uses NADH, exactly. And the two good things we get out of complex 1 through that high energy electrons and NADH is both you got so pumping some protons into the intermembrane space as well as making more ubiquinol. Exactly, perfect. And then that ubiquinol can, of course, go to your complex 3 to pump more protons as well as make some cytochrome. Cool, so like that's it. Honestly, like you guys just said all the key testable points, and if you know those key testable points, you're going to be good for test day. And like, yeah, they might get more granular on the test, but if they do, they're most likely going to give you a passage on it, and they'll really kind of like have a lot there for you to use. But those are by far and away the most testable stuff. And so that's what I'm going to focus on today, because that's what matters most for the MCAT. Like you already have enough crap to memorize. You know, don't work on memorizing a bunch of other stuff that, you know, might give you a point or two on test day if it's not necessarily the most important. You know, like, and so to be totally honest, Esther, the more you know, the better. You know, like, I'll be totally honest, if you know everything about the different forms of cytochrome, it could help, but, you know, the ability of them to test that versus the bigger picture steps is just not as likely. It really isn't as likely, and that's one thing that we've noticed, not only from the old MCAT, but even, like, looking through the new sample tests and all the different questions they're writing, they tend to make questions that are actually easier than you would expect. It tends to like look very complicated, but the actual guts of what they're testing is generally a critical thinking concept in figuring out what they're asking, but it's usually something fairly surface level in terms of metabolism. It's nothing like what you'd see in an actual metabolism final in college. It's very, very different. And so that, if there's one thing to know about the MCAT in general in terms of prep, you want to go in with a shotgun approach. You want to know a very, not a little bit, but not a very little bit, but a little bit about every single possible thing that's in science. Like all of it, but just an inch deep. Like you don't have to go too deep, but you got to know a little bit about every single possible little thing. And so exactly, there we go, Brianna. That's exactly that's what the MCAT's all about, to be totally honest. It really is. And that's exactly why reviewing full lengths are so important, especially once you guys get access to those AMC full length exams, which is going to happen in less than a week. I was speaking to the manager of content, and I talked to him earlier this week, and he promised me it was within a week we were going to get it. So I was like, yes. But with that in mind, don't take it until about a week or two before your actual MCAT. Don't take it soon. It might have happened yesterday. Cool. He told me it was early this week that it was going to happen, so it might already be out there now. Perfect. Sweet. You guys got it today or yesterday. Awesome. See, he told me the truth. I knew it. All right. So it's up there. Just don't mess with it yet. What you will want to use, which isn't up there yet, you're also going to get access to the AAMC question pools. I'm thinking the AMC's already written them. Liz and Andrew and Patrick might know. But that's another resource that the AMC is also creating up as well. They're already, okay, cool, they're already there? Sweet. Oh, sweet, they're up as well. Okay, so those, if you want, you can actually hit those earlier. Just don't touch the sample test, like the actual full-length AMC exam, until like 2 weeks before. But yeah, if you want to hit the question pools, you can hit those sooner. But I'd probably do it within maybe 6 weeks to a month of your MCAT, you know, like put it a little bit closer. Wait till you feel pretty confident in all the resources. But yeah, hit that stuff soon. And that'll really show you what I'm saying about how the questions are actually more straightforward than you expect. Vast majority of them are a lot more straightforward.
Yeah, exactly. I was going to say, yeah, if you're testing in April, then you should do it right now. Yeah, I would. If you're testing in April, I would hit this question pool starting now. I would wait about a week or two and then hit the sample test. But you got it. Yeah, it's the same. You know, Ian, I haven't looked at it. I think they're discrete questions. I haven't looked at that resource yet. I've only looked at the sample test in terms of like the actual like the legit way that it's presented and all that stuff. So it's pretty cool. But I do know it's discrete questions, so I assume it is. You got it. Okay, it is cool. Yeah, the sample test is definitely passages in discrete. I haven't seen the new thing, the brand new thing, but cool. All right, let's. So if you have questions on any of that too, and I know a lot of you guys are testing in April, so if you do want to talk shop about full-length exams and like why I have this thing, I'm not sure if I should take this exam or this exam, hit us up in the Q&A. We can talk for days about all that kind of stuff, and to be honest, that's some of the most important stuff to make sure that you're really prepping effectively, and the most effective way to prep is to take full-length exams. It really, really is. Just make sure you're really reviewing them. That's key. All right, so with that out of the way, that was the biggest guts of today's class was electron transport chain, so check that one off the list. Second thing to talk about is what we use it for, and that's the oxidative phosphorylation. So I guess the big thing here is this is a very, very, very fancy pump. It's really cool. It's one of the most kind of amazing things that's I think exists in terms of nature. But so the whole idea is this is the intermembrane space down here. And so once again, what do we know about the intermembrane space at this point? What would be true about it? A couple things you could say. Low pH, perfect, you got it. So it's low pH, it's super acidic. There's basically a super high concentration of protons. And so we've got two different regions of your ATP synthase, right? First part here, of course, is the F0 portion. It's basically an ion channel. So it's the membrane spanning portion of your ATP synthase. And so what, of course, your protons are going to do is they are going to move through F0 into F1. F1 is the exciting part. This is the part that actually utilizes the electrochemical gradient to actually create ATP. So that's your F1 portion. Now, one thing that I want to let you guys know, and these are little pictures of protons, they move through, and of course, it creates energy through a mechanism, and this is funny, but we actually don't really know yet. It's actually still a matter of debate among biochemists and the specifics of how this works. Now, there's generally accepted theory that we mostly believe, and it's called chemiosmotic coupling, where it becomes basically a thermodynamic issue. So what it is, of course, through the releasing of the protons down their electrochemical gradient. So remember, they're leaving not only because there's a high concentration of protons in the intermembrane space, but also because we've built up more positive charge in the intermembrane space. So they're being sucked to the relatively more negative charge in the matrix, as well as the lower concentration of protons in the matrix. So doing that actually releases a ton of energy. In fact, it releases about negative 220 kilojoules per mole of energy of protons. So that's a mole of protons, which is a ton of protons, right? So we're not talking a single pump here. We're talking big scale. That number, to be totally honest, I'm kind of curious if Liz and Patrick and Andrew think if that's something worth memorizing, that negative 220 kilojoules per mole. I know I've seen it show up before. I think it might be worth knowing. I would know at least it's a pretty big number, around 200, But yeah, as Patrick says, it could be fair game. I'm not sure if they're going to specifically test it by number. No, though, think about that. That's 220 kilojoules. So that means 220 times 10 to the third power. That is a ton of energy. Like, that's a ton of energy, right? This is a very, very, very energetic exergonic process, you could say. And so the idea is that it requires a lot of energy to create ATP, and so it takes a bunch of energy through letting these protons move through their gradient. But yeah, exactly. Think big picture. Yeah, so Esther's got a good point there. We're actually going to hit that in a second. So we'll have a little summary slide where I'll get to that point, though. Because, yeah, I've seen 36 as well as 38. It actually depends on which type of shuttle system you use and whether you're eukaryote or prokaryote, which is the difference. Cool. Yeah, exactly. Yeah, I agree. It won't be a major thing being tested. But it's a lot of energy. It's a lot of energy. We like to give you, exactly. We like to give you the extra info. All right, so that's one way. It's called chemiosmotic coupling. Basically, you couple the energy loss through moving the protons down the gradient through the creation of ADP into ATP. So there we go. It's 220 kilojoules per mole. As we said, it's very exergonic, which of course then creates ATP and leaves. I'll do that once again just because animations are super fun. Look at that animation. There it is. Pop, and then we get ATP. Now, that's one of the theories. There's actually a second theory that people believe is actually creating ATP, where it's not straight chemiosmotic, it's not straight a thermodynamic thing, but it's actually more of a conformational thing. And so actually we said this again, just a real recap, remember, the creation of ATP is endergonic, right, requires energy. Thus, of course, protons moving down the channel is exergonic, releases energy. All right, so the other theory is called conformational coupling, where basically the movement of protons through just literally shifts this enzyme into the right conformation that forces ADP and ATP so close together that it basically forces it to stick. This actually says that it's more of like a turbine where it's actually cycling through. Energy enters, rotates, changes the conformation. Notice that it basically is squishing your ADP and ATP so close together that it forces a new phosphate bond. Yeah, Brandon, that's the thing. I didn't realize that it was actually still up to debate, but depending where you go to school and what your teacher basically likes more, they'll either talk about conformational coupling or chemiosmotic coupling. I actually didn't even know that it was debatable until I started teaching biochem. I was like, oh, cool. But rumor has it, people like chemiosmotic more as a general rule. So since it's up to debate, know them both. You don't know what the AMC is going to get into. And honestly, if this gets tested, I would not be surprised if it was in the context of a passage where it talks about both of them and you have to infer basically what theory they're getting at according to the question stem. That's a super common theme, and I'm sure you've seen this already in passages where it gives you two alternate theories that are argued and it makes you basically analyze the both of them. Totally true, Lauren. That would be a very AAMC thing kind of thing to do, if you know what I mean. So cool. All right, so that's the two. Basically conformational, basically the energy causes a shift. Notice it squishes them together, forms ATP, and that process keeps repeating. I've literally heard that it's basically the same as like an engine turbine spinning. It's a pretty similar process. All right, so that is the entirety of our cells, well, through, of course, what Rebecca talked about in the previous class, but how we create energy through these different processes. All right, so here's just a little summary, as we said. And actually, I'm going to open up this whole thing. I want you guys to actually show me one thing that you would personally change if you were going to redraw this. And there's one thing that I would actually slightly edit here. I'll fill up the whole thing. And this is just a summary if you want to basically take it. I'll put that. There we go. Ah, agreed. Complex 3. Well, there's one thing I would say. Well, first of all, complex 3 happens twice. Make it 1 and have it happening, looping it through itself. Also, what I would say, where do the electrons from complex 1 go? Do they go into complex 2? Where does that? No, ubiquinol goes into complex 3. So you'd want to jump over that. And so it's actually, you got it. So the high energy electrons from complex 1 go to complex 3, just like the ones from complex 2 to go to complex 3 as well. So that's a little trick that I noticed, at least. But this is how it's generally, this is like one of the textbook classic images just showing how electrons get passed down the chain. Exactly. I don't think there is, Esther. I don't think there's no docking sites on 2, unless if Andrew or Liz has them, at least not in terms of the big picture stuff that I was told was the most important stuff to hit today. At least it doesn't, we don't create cytochrome in complex 2. You know what I mean? And that's what we use your ubiquinol to do, is to reduce cytochrome. That's not till you get to complex 3. So, yeah, Andrew hasn't heard of any either. So, yeah. The thing is, almost always, just as a general rule, things are always more complicated than they seem. And so often there actually is something there that we're not aware of. That's usually some kind of, maintains consistency. It's like kind of like a endocrinology thing. It's, we like to say that this leads to that, which leads to that. But in reality, there's so many signaling cascades that it's actually quite a bit more complicated. But this is the very broke down, very simple image is the way to think of it. So. All right, so that's a little summary showing all the protons moving and the electrons moving down the line, namely focusing on things like NADH is affecting complex 1, FADH2 is complex 2. Notice complex 2 is not pumping protons, whereas complex 3 and 4 are. So that's more of the big picture stuff to focus on here. Cool. All right. Actually, here's another important thing that you do want to memorize for the MCAT, though. So on average, you get 2.5 ATPs per molecule of NADH. You get 1.5 per FADH2. So that you do want to know. That is something that can actually show up on the test quite a bit. And so if you want to screenshot, snag that guy right there. Additionally, we'll kind of talk about the total numbers because that's one thing Esther was saying a second ago about 32 versus 36 and 38. So let's talk about that and kind of get into the whole shuttle systems and how they could be different. All right, so this is review from what we talked about in Rebecca's class. Glycolysis, of course, net produces 2 ATP. Remember, in actuality, you're producing 4, but it requires 2, so we're just going to do net stuff here. So, of course, 2 ATP as well as 2 NADH. That's where we have the little asterisk there, and I'll get into that. That's the different types of shuttles. Pyruvate decarboxylation, we create, of course, two NADHs. And why don't you guys tell me? So in citric acid cycle, what do we make? Remember, you got two molecules of pyruvate entering, so let's account for both of them. 6 NADHs, nice, as well as, well, 2 FADH2s, right? Because, accounting for, of course. Yeah, you got it. If we're going to do both of them, as well as 1 GTP, but since it happens twice, you get 2 GTPs as well. And remember, your GTPs get turned right into ATP. So yeah, it's GTP, but we can just turn it into ATP, as we said in the last class. So there's your total numbers. So then using the numbers that we have here to be very realistic with everything, notice, of course, you get 2 ATP, that's total there. On the 2 NADHs, though, this is where we have to talk about the shuttle systems. So you can either get 5 or 3 ATP because remember the NADH that you make in glycolysis, it can't go directly into the mitochondria, right? Like you can't just transfer NADH directly into the mitochondria. So you have two different types of shuttle systems. You guys know the names of the shuttles? I don't know if we got into it in the other classes. Nice, malate aspartate, and as well as, there's one other one, nice, you guys know it. Close glycerol 3-phosphate's the other one, Sarah, nice work. So it's either the malate aspartate shuttle or the glycerol 3-phosphate shuttle. Which one is more efficient? Is the main thing I would want you to know. Nice, malate aspartate, exactly true. So the malate aspartate actually still gets your pure 2.5 ATPs per. If you do the glycerol 3-phosphate shuttle, then you only get 1.5, which is why you get the 3 there. So mostly no, the malate aspartate shuttle is more efficient. You get more ATP if you use that type of shuttle system. Cool. All right, so that's big picture stuff right there. Pyruvate decarboxylase, notice once again 2.5 per, and then going through, we can kind of keep going down the line, which then would give you 30 or 32, which of course, notice it's super arguable when you get to the total number that you're talking about here. What would be one thing that I would say for prokaryotes? And I've seen a bunch of different numbers here too, Esther. And also it's changed. They used to say that it was 3 ATP per NADH as well as 2 ATP for FADH2. That's often why we get a different number. That was they kind of, I think it was a more recent discovery where they realized it was actually the 2.5 and the 1.5. Yeah, so exactly, I would say, well, prokaryotes get more, I would say first and foremost. So yeah, I'd say 32 instead of 30. Why would prokaryotes get more than eukaryotes like us? There's one good reason you want to know here. Bingo, there's no shuttle. There's no membrane-bound organelles to have to move stuff back and forth. And so, of course, that's why, prokaryotes will get more than eukaryotes as a general rule because they don't have to worry about moving things across membranes. Yeah, I don't think so, Esther. And that's the thing, too, because I know we used to always say 36, but I used to always say, this is like back in the day, that NADH always gave you 3 ATP and FADH2 gave you 2. And then I think it was maybe like 4 or 5 years ago they kind of started changing those numbers, but I'm not sure. I don't research biochem, so I don't know the actual studies and where that came out, but I do know the numbers generally accepted now are lower than we used to say a couple of years ago. So kind of irritating, but yeah, I wouldn't imagine that they would actually give you like 30, 32, 34. This is the most recent though. Like if you look at the most recent biochem textbooks, they mimic this kind of general thought, which is why this is a pretty brand new class. We just wrote this about 6 months ago maybe, and so it's pretty up to date. So. But yeah, if you're taking biochem right now, you might have more. And if you want to get real nitty gritty because you got a biochem test next week, hit us up in the Q&A. We get really nitty gritty with you. Yeah, I totally agree, Lauren. Oh my God, that's one of the problems is everything changes. Oh man, it's kind of irritating. But oh well, at least we don't work in particle physics. I feel like that changes even more. So pretty good there. All right, so we're going to bring up a poll. We're going to have you guys do this. As I said, the main focus of today's class was very much to talk about thank you very much. I appreciate bringing that there. The electron transport chain and oxidative phosphorylation. The very last bit, we're going to talk a little bit about gluconeogenesis and glycogen, but namely, we're just going to talk about how it's different than glycolysis. We'll give you the names of the enzymes and do a little review. All right, so answer this one first, though. This is the kind of way you'll see this stuff tested. They call that product placement. You will probably see it in your social psych classes. Right, Brandon? Oh, man. Actually, cars, they do a lot of, as you probably noticed, there's a lot of advertising type stuff in cars. It's pretty common. Yeah, I was going to say, that's why it doesn't even matter, right? Yeah. All right, so there we go. Most people have already voted. We do have 71% of you going for answer choice B. Nice work. So why would it not become 0 if you can no longer, notice, use complex 1? Bingo, Maya. FADH2. What's FADH2 going to use? Complex 2, exactly. Now, remember, though, what would you rather lose, complex 2 or complex 1, given the numbers that we just talked about? I'd probably rather lose complex 2 because we utilize a lot more NADH, as you can see from the previous slide, than we use FADH2. And so, like, you're pretty screwed if you can't, and basically this would mean you can't use any of your FADH2. Oh, yeah, that's a good point. Oh, good point, Sarah. You need complex 2 for Krebs, and if you broke the Krebs cycle, you'd be really screwed. Oh, I wasn't thinking that, Sarah, Brandon. High five. Smart move. Totally true. So yeah, basically you'd be in trouble no matter what. So if any part of your metabolism breaks, you're in trouble as a general rule. I think we'll kind of just stick to that. It's so true. Yeah, see? You guys caught me. Totally got it. All right. So main idea, of course, as we said, pumps electrons across the inner membrane while oxidizing NADH, not FADH2, which means, yeah, it's going to reduce it, but it won't be 0. All right. Good work, team. All right, we'll do one more, and then we'll, as we said, talk about 10 minutes or so about gluconeogenesis, mostly just hitting key enzyme names that are different than glycolysis. Another 10 seconds or so. We've got most of the votes in. Pretty split on this one. Not nearly as strong as we were in the last one. So I'll start talking it through. Put in your votes so if you haven't voted yet. So this is the stuff that really happens at the MCAT, is that it's being very careful with what we're focusing on. So we're looking, of course, comparing the intermembrane space to the matrix. So basically, would the intermembrane space be more likely to be positive or negative? The intermembrane space. Bingo, positive because it's got lots of protons. That's, of course, the first and most important thing. So if we know that's going to be positive, get rid of B, get rid of C. It's going to be either A or D. Nice. And so then what happens, though, as you generate ATP, what's happening to the charge? Will it be going up or going down? And there we go. The poles are getting very consistent now. Got a lot of people saying that it goes down because protons are leaving. And so then what's happening to the intermembrane space's pH as protons leave and go to the matrix? It goes up. Gotta be so careful with that pH thing. People swap that all the time. Like if there's one silly mistake that we see all the time in physical sciences or chem phys, really it's that pH thing. So yeah, the pH goes up because of course the protons are going down, thus it's becoming less acidic. So be just real careful with that. If there's one thing that I do recommend every time that you want to just double check your answer, probably anything that deals with pH would be the place to do that. All right, so what we're going to do for the very last part of class, as I said, main focus today was ETC and, of course, the proton motive force. We're just going to talk about how glucogenesis, glucogenesis, of course, is different than glycolysis. All right, so let's kind of jump into this. So remember, of course, glycolysis, we covered this in the last step. There's a couple key things that we need to be aware of, namely the steps in red. Why do we talk about these red steps so much? Why are they red in the first place? They're the irreversible steps, right? So I know Rebecca talked about this last class. These are the ones that, of course, you need to memorize. You got it. Yeah, you can't turn back. It's a great way to say it. You got it. All right, so we'll kind of go through all of these. So glycolysis and pyruvate carboxylation, of course, these are the steps you can't use. First is hexokinase or glucokinase. Mostly that's just liver stuff, though. What about the next one? Fructose 6-phosphate to fructose 1,6 bisphosphate. This is your most important to memorize of them all. PFK1, phosphofructokinase 1. That is your control point. If there's one thing to memorize in glycolysis, it's right there. It's where it's at. All right, so then after that, of course, we move into your PEP, phosphoenolpyruvate, into pyruvate. We'll kind of just flip through the rest of these. You got pyruvate kinase, right? Nice work. And then, of course, the last one, pyruvate into acetyl-CoA, is your pyruvate dehydrogenase complex. You got it, yeah. So PDC, pyruvate dehydrogenase complex, exactly. Cool. So know those. If there's 4 to know, those are the 4 to know. So since these are the irreversible ones, we're going to talk about the 3 that you need to do to get around those steps. So you got 3 enzymes that you want to know now about them. Notice that we're just bypassing these same steps. So notice what we'll do, of course, is the very beginning, we can talk about using oxaloacetate and then plugging that in. All right, so of course we've got a pyruvate. We use it to make acetyl-CoA with pyruvate dehydrogenase complex, as we said. But we can't turn acetyl-CoA back into pyruvate. That is impossible. So instead what we do is we basically take our pyruvate and turn it into oxaloacetate. So notice we're basically adding CO2. And so now the cool thing is this would be pyruvate carboxylase. Now you use biotin as a cofactor here, but I'm going to focus on the word roots because that's the easiest to test and the easiest to apply as well. So notice pyruvate carboxylase, thus of course we're adding a carbon in the form of CO2 to pyruvate, which means how many carbons must oxaloacetate be? This is kind of the easier way to test this stuff. Got to be 4, right? Pyruvate's 3, so stick on an ATP. Notice this is an endergonic reaction, right? It requires ATP to add that CO2 there. So we use ATP to basically stick that guy on there. Then, of course, still requiring energy, notice now in the form of GTP, we use our PEPCK, that's phosphoenolpyruvate carboxykinase, right? Of course, is going to now remove that carbon. In fact, it's the same CO2 that we added with your pyruvate carboxylase gets chopped off, forming PEP. But now notice, of course, we do have a pyruvate, or not a pyruvate, kinase, so a phosphate there. Sorry, I was like, phosphate group has been added. Hence kinase. As always, kinase means moving phosphates around. Once we've got our PEP, so notice these are your 2 things to notice that are different here, right? So pyruvate carboxylase, this is unique to gluconeogenesis. PEPCK, also unique to gluconeogenesis. Then once we get up here to fructose 1,6-bisphosphate, the names get super easy because they're just described by exactly what they're doing. So to turn fructose 1,6-bisphosphate into fructose 6-phosphate, all you got to do is basically add an A's. Exactly, totally true. It's what we're doing here. And notice we're skipping all the multiple steps that are reversible because it's just the same thing that you had in glycolysis. So of course, same thing, fructose 1,6-big phosphatase, exactly as Esther said, which of course means we're going to chop off one of those phosphate groups. So you chop off the phosphate group, gives us fructose 6-phosphate. And so then fructose 6-phosphate, though, if we want to actually make this into glucose, of course, we're going to need one more step. Well, of course, there we go. Oh, actually, before I move on, one thing I do want to point out, this is probably one of the big key take-homes too. So remember, as we said before, PFK1 is the rate-limiting step in glycolysis. Notice that fructose 1,6-bisphosphatase is the rate-limiting step in gluconeogenesis. So if there is 2 things to know, these are the 2 things to know about gluconeogenesis as well as glycolysis because it's the rate-limiting steps. They're both irreversible, so of course you need to circumvent one to use the other. All right, so notice you're using water to basically chop off phosphate. So what do you call an enzyme that uses water to chop something off? Hydrolase, right? So it's a type of hydrolase. Nice work. And totally, yeah. We'll do one more question after this. But so then after that, we've got our glucose 6-phosphate. Once again, using a hydrolase, turns it into, of course, glucose. So notice once again, glucose 6-phosphatase. Just add an A's, which means you're going to chop off your glucose 6-phosphate's phosphate, which of course then leaves us with glucose. Nice work. All right, so now one thing that we do want you to be aware of here as well, notice that glucose 6-phosphatase is only expressed in the liver and kidney because this is the place that what happens? In fact, we talk about this a bunch in the kidney class as well as some of the other classes. It's the only place that gluconeogenesis happens, exactly. And so that's why we only have glucose 6-phosphatase in the liver and kidney. But glucose 6-phosphate, what could you turn glucose 6-phosphate into if you didn't want to turn it into straight glucose? Maybe in skeletal muscle specifically. Glycogen, exactly. So then you can turn your glucose 6-phosphate, though, directly into glycogen without making it into glucose first. So if you did need to do that, you can use glucose 6-phosphate for other stuff. Nice work. All right, so glucose, of course, then goes to the blood. As we said before, glucokinase. This, remember, where's glucokinase, though? Glucose kinase is only made in one place, too. That's liver, exactly, you got it. So glucokinase is in the liver, so of course that's why we're specifically referring to glucokinase here, because we only have glucose-6-phosphatase in the liver as well. All right. So there, if you want a screenshot, here's your screenshot that sums up both glycolysis, pyruvate carboxylation, and how gluconeogenesis is different. Honestly, these enzymes in the red circles, memorize them, know them. They're the key steps, right? They're the irreversible steps. Oh, it's Command-Shift-4, Dana. Yeah, Command-Shift-4. All right. Let's, oh, actually, we did it there. Cool. All right, that brings us pretty much to the end of it. Actually, there's one more thing we'll show you before we get. So notice then, this is kind of like our last thing before we jump into our next class here. So notice that glucose can go into circulation, but remember, this isn't the only source of energy, right? So the other sources, you could use lactate, you could use TCA cycle intermediates that we talked about before, you could use amino acid and carbon skeletons. Now, I do want to let you guys know, though, all of this stuff is covered really in depth in your third metabolism class where we talk about alternate energy sources. And so we're not going to get into it today, but check out Metabolism 3 when it's offered next. There is more, I know, Ariel. We're not doing it today. We're done with metabolism for today. We're going to jump into, whatchamacallit, organic chemistry next. But do check out Organic Metabolism 3 where we talk about the rest of the actual control there. All right. So, and yeah, I know, right? There we go. So glycerol, lactate, TCA. Let's talk about glycerol. Where do you think you would get glycerol from? That's one thing we didn't talk about yet. This also, though, yeah, that's from breaking down fats, right? You break down a triacylglycerol, and of course you're going to have glycerols floating around, which then you can turn them themselves, of course, back into glucose if you need to as well. You got it from fatty acids directly into DHAP. Totally true, Sahar. Nice work. Good memory. All right, so we'll call it quits for today in terms of metabolism. I hope you guys got the key take-home points, the most important, testable, big picture. After this, of course, we're going to come back and we'll do some organic chemistry. But we'll take a short break. I'll catch you guys very soon. Make sure you grab the recaps on the next slide as well. All right, take care.